Hello grade 12 and welcome to our term 2 summarized video. Okay, so in this video we are going to go through three big topics. The first one is work, energy and power. The second one is the Doppler effect, and the third one is chemical changes. And within chemical changes we will talk about rate and extent of reactions, chemical equilibrium, and lastly acids and bases. We will briefly mention the chlor-alkali industry, the equation that is involved with this, and the different products and what these products are used for. Just a few examples. Okay, so let's start. Work done is when a body is made to move by a force in the direction of the force applied. You can represent work done as the formula F, which is your force, times delta x, which is the distance over which the force will act, times cos theta, which is the angle at which the force will act. Now, if the force applied acts in the direction of the displacement, the work done is positive. If the force applied acts in the opposite direction of displacement, the work done is negative. If the force acts at a 90-degree angle to the object, there will be no work done, and we will see this in an example just now. Here is a very simple diagram that shows us the different types of forces that can act on a body. Okay, so you can have the weight acting on the body, the normal force acting on the body also, and then a force of friction, a possible force that can act on the body, and a force that is applied, so in this case a pulling force acting at an angle theta, which is 20 degrees. And let's assume, for instance, that this box now moves for 20 meters. Okay, work done by the force applied will be your 100 newtons times the distance and times the cosine of the angle at which the force is working, and you get the work done as 1879.4 joules. Now, work done by the force, the normal force is 0 because it is acting at a 90-degree angle to your object. Work done by the weight is also 0 because it is acting at a 90-degree angle to your object. Now, work done by the friction is there's a 2.5 Newton force there, so you have your 2.5 times the distance and times the angle in which this force is acting. So this force is acting in the opposite direction to the direction of motion, so we have a 180-degree angle. Now this gives us a negative 50 joules, which represents a negative work done. The types of energy that you need to be familiar with is mechanical energy, kinetic energy, and gravitational potential energy. Now, your mechanical energy is the sum of all kinetic and potential energy. Kinetic energy is given by half times the mass times the velocity squared, and gravitational potential energy is given by the mass of the object times gravity times the height at which the object is. Now, the energy that is associated with work done by a net force usually transfers into kinetic energy when the body starts moving. Okay, so the work energy theorem comes in and helps us state this transfer in a mathematical equation where your net work done will be represented by the kinetic energy at the final stage subtract minus the kinetic energy at the initial stage, okay, which can be represented as delta EK. So delta, the change in kinetic energy. Now remember, just like work, energy is a scalar quantity and will also be measured in joules. Let's look at this simple example. So we have a very simple diagram here with a trolley that is being pulled up with a force of 50 newtons, and then this trolley has a mass of 1.5 kilograms. There's a friction force of 10 newtons. This is an elevated ramp. It's elevated at an angle of 25 degrees, and the distance of the ramp is 8 meters. So if you are asked to calculate the net work done by the force that is pulling this trolley, you will go in and you have to start by identifying all the forces that are acting on your body. Now we already know that any force acting at a 90-degree angle will have a 0 work done, so you don't need to calculate for those. And now you will only be left with the applied force, the friction force, and the component of the weight, okay, that will be acting on your object. So let's start with the work done by the force applied. You will have your 50 newtons times the distance times cos 0. Now why cos 0? The force is not acting at a certain angle. It is straight up pulling this trolley, right? So you have a 0 angle where your force is being applied. This gives us a work done of 400 joules. Now work done by the weight, you will have to go in and again resolve your forces so that you can apply the correct component of your weight. Now which component of the weight is actually acting on your object as it is moving upwards? The weight will be pulling it downwards, but now remember, you can't take the weight in this direction. So you have to resolve that direction into your x and y components. Okay, so in this case, our y component is represented now by the weight cos 25, and our x component represented by the weight sine 25. Now remember, the line or the side of the triangle that is opposite your angle will always be the sine, and the line of the triangle that is touching your angle will always be the cosine. Okay, so that will be weight sine 25. And now in which direction is this weight working? Okay, so the trolley is being pulled upwards, but the weight will be tending to pull the trolley backwards, right? So down, so it will be going in the negative direction. Okay, so that will be a negative sine 25, and then you calculate your weight, which is 1.5 times 9.8 times the distance that the trolley will travel, and that gives you a negative 6.2 joules. The work done by the friction, again, this is another force that is acting in the opposite direction to your motion. Okay, so you will have your 10 newtons times the distance times cos 180. So it is going in the opposite direction. So it is now, instead of the applied force was at a 0-degree angle, the friction force is at a 180-degree angle, so the complete opposite. And this gives you now a minus 80 joules. So your overall work, your net work done, will be given by 400 joules minus 6.2 minus 80, which gives you 313.8 joules. Conservative and non-conservative forces. A force is conserved if the work done by the force to move an object from one point to another is not dependent on the path taken. Once again, please use the correct terms if you are asked to state or to define a conservative force. Make sure you mention the keywords that are underlined. Now, a non-conservative force, if a force is non-conservative, then the work done by that force to move an object from one point to another will depend on the path taken. Now, examples of conservative forces, you have gravity, force of gravity, force in elastic springs, electrostatic forces between charges, magnetic forces, and you can find more. Examples of non-conservative forces, the most common ones will be friction, tension, air resistance. Mechanical energy. Now, we have already mentioned that mechanical energy will be the sum of your potential and kinetic energy. If a body is free falling, you would demonstrate conservation of mechanical energy by the conservative force, in this case gravity, as your overall mechanical energy initially to be equal to your overall mechanical energy at the final stage. Okay. If they are not equal, then you have non-conservation of mechanical energy. Now, in a body that is acted upon by a non-conservative force, the mechanical energy will not be conserved, obviously. So if your mechanical energy is conserved by conservative forces, then obviously the opposite will happen when you are dealing with non-conservative forces. The force that acts in the direction of the motion will increase the mechanical energy, and the force that acts in the opposite direction of motion will decrease the mechanical energy. So this means that when you are to calculate the net work done, and there are different types of forces that can be acting in your system, you will need to take into consideration all your non-conservative forces, all your conservative forces, and represent the possible energy transfers that might have occurred in your system. Now, all of this can be represented mathematically using the following formulas. So you will start by stating your net work is equals to the change in kinetic energy, because as soon as there is a net force acting, there is work done, and then the body is moving, so there is also a change in kinetic energy in the body. Now, if your work done let's say is impacted or is affected by conservative and non-conservative forces, you can now represent those forces by having work done by conservative forces and work done by non-conservative forces still equal to the change in your kinetic energy. Now, these non-conservative forces, obviously, if there are any in your system, you can make that the subject of your formulae, and your non-conservative force, let's say your work done by non-conservative forces will be equal to the change in kinetic energy minus your work done by your conservative forces. Now, here is a special consideration that you need to also keep in mind. If you are only conservative force in your system is the force of gravity, which is always kind of going to be the case for you, then your work done by the non-conservative forces is equal to your change in kinetic energy minus the negative change in potential energy. And why is it negative? When the body is moving upwards, the force of gravity is working against the motion, so that will make it negative, okay? But if the body is moving downwards, then the force of gravity is working in the direction of motion, so it will be a positive. So you have the change in kinetic energy minus the change in potential energy. Last in this topic is power. So power is defined as the rate at which work is done, or the rate at which energy is transferred. Mathematically, you will represent power as P is equal to your work done divided by change in time. Now, if there is a constant force that is applied and the motion is in the direction of your applied force, you can also find power by multiplying the force times the velocity. Now, if the force is not constant, you can find the average power by multiplying your average force by your velocity. Please note that in this case as well, if you have conservative forces acting or non-conservative forces acting, you can represent that in your work done, and then you place your work done, your net work done, into your power formulae. The second topic in your term 2 is the Doppler effect. Now, if you are asked to define the Doppler effect, please make sure that you use the correct terms, okay? One simple way is to say the Doppler effect is the perceived change in frequency of a sound that is caused by either the listener or the source moving relative to each other, okay? It's very important because it is based on how the sound is moving either towards or away from the listener, or the listener is moving either towards or away from a source, from a sound source. So you have to mention that this is relative to each other. Now, the equation for your Doppler effect is mentioned here, where your V represents the sound in air, your VL represents the velocity of the listener, your Vs represents the velocity of the sound, Fs represents the sound frequency, and then your velocities of the listener and the sound source will be either positive from the listener to the source or negative from the source towards the listener. I have picked up on there's a little bit of confusion when you are to determine the sign in relation to either the source moving, the listener moving towards or away from the source, or towards or away from the listener. So here again is a very simplified summary. The direction. If the source moves towards the listener, the velocity, the Vs, will be negative. If the source moves away from the listener, the velocity of your sound source will be positive. If the listener moves away from the source, then that velocity is negative. And if the listener moves towards the source, the velocity is positive. Now also in your Doppler effect equation, this equation can be rearranged depending also on if you have a stationary listener or a moving listener or a moving sound source. Okay, so let's go through this. If you have a stationary listener and the sound source is moving towards your listener, remember now that your velocity of your listener will be 0 because he's not moving, he or she is not moving, and the velocity of the sound will be negative because it is moving towards the listener. So if you place that into your equation, this will be the equation that you will use. So you will have the frequency of the listener being calculated by the speed of sound divided by the speed of sound minus the speed of the sound source moving towards the listener. Okay. Now remember, speed of sound is a constant value, and you will usually be given this in your formula sheet. You will multiply this by the frequency of the sound in your specific question. Now, if the listener is stationary and the sound source is moving away from the listener, then the speed at which the sound source is going is going to be positive, so it's going away. But again, the speed of the listener is 0 because the listener is not moving. And then you replace that in your formula. You see, instead of a negative, you will have a positive because the speed of the sound now is positive. Okay, now if the sound is stationary but the listener is moving, now here the listener is moving towards the source. If he's moving towards the source, the velocity of the listener is positive. Okay, and you will place that in your formula. Now notice that there is a change that has happened. Your frequency of your listener is now calculated by the speed of sound, the constant, plus the speed of the listener divided by your speed of the sound source. Okay, and if you have the contrary will be for if the listener is moving away from your source. Again, your speed of your listener will be negative, and then you will represent that in your formula. The next part is to discuss the Doppler effect and light. Now, when it comes to your visible light spectrum, I suggest and recommend that you learn these colors in order. Use the acronym ROY-G-BEEF to help you remember red, orange, yellow, green, blue, indigo, violet. Okay. Now, the next thing you want to remember is that red will have the smallest frequency and the highest wavelength. Okay, so your wavelength goes downwards, decreasing, and your frequency goes upwards, decreasing. So violet will have the greatest frequency, and red the smallest frequency, and violet the smallest wavelength, and red the highest wavelength. Okay, if you can remember this, any question that is asked to you, especially relating to the movement of stars, you will remember that if the star is moving maybe towards an increasing frequency, and you know that in terms of frequency, red will have the smallest frequency while violet will have the highest frequency, and blue is more towards violet, so blue will have a higher frequency than your red. It means that that star is moving in towards the blue, so it's going in the blue, is having a blue shift. But if they tell you, for example, that this star is moving towards the lowest frequency, then it will be moving towards the red, and that will be a red shift. Okay. If the star is moving, even if you are not sure, if you can calculate the wavelength, or if you are given any information about the frequency, you can easily determine whether it will be a blue shift or a red shift by using this information over here. Okay, so please write this down and use this appropriately. Another way you can also say it will be the shorter the wavelength, the higher the frequency, and therefore this star is moving towards something. Okay, so if it has a shorter wavelength, it is moving towards. If it has a greater wavelength, it is moving away from. So depending on your reference. Two applications of the Doppler effect that you can state is the Doppler flow meter, used to detect the speed of blood, the Doppler radar, used by weather stations to help predict the weather, or radar guns used by the police in traffic. Our last topic for term 2 is chemical change, and within this topic there are specific units that were discussed. You had your rate of chemical reactions, chemical equilibrium, acid and base reactions, okay, and the chloralkali industry. So what is a rate of chemical reaction? This is defined as how fast or how slow the concentration of the reactants or the products will change. There are specific factors that will affect the rate of a chemical reaction, and these factors are the nature of the reactants, the surface area of the solid reactants, the concentration of the liquid and gas reactants, the pressure on the gas reactants, the temperature at which the reaction is taking place, and the presence or the absence of a catalyst. Now, for any chemical reaction to occur, there are specific things that need to happen, and these are briefly summarized within the collision theory. Okay, the collision theory considers the reacting particles, and these reacting particles need to collide first of all, and then these collisions need to happen with enough minimal energy, which can also be called activation energy, and they need to collide with the correct orientation. To measure the rate of a chemical reaction, because there will be different types of chemical reactions, and each of these reactions with their very specific characteristics, there are ways or tell signs that you will use to determine how fast a reaction is going, and some of those will be gas released, so you will measure how much gas is being released, or there might be the formation of a precipitate, so you will go ahead and measure the rate at which this precipitate appears, and then you can also measure the rate of color change in your chemical reaction. Some chemical reactions can release energy into their surroundings, and some will need energy from the surrounding. And these chemical reactions can now broadly be classified as either exothermic reactions or endothermic reactions, where your exothermic reactions will be the ones that release energy into the environment, and your endothermic reactions will require energy from the environment. Also, in your exothermic reaction, your reactants will start at a much higher energy level, producing or giving off products with a much lower energy level, while your reactants in your endothermic reaction start at a very much lower energy level. They get all this boost of energy from the surrounding, and then they produce products with a much higher energy level. Now, when it comes to gaseous mixtures or gaseous reacting molecules, the energy of your individual molecules or individual particles varies. Okay, so now the Boltzmann's distribution comes in to help us represent the specific number of particles that have enough energy to be able to react in a chemical reaction. Okay, and your Boltzmann distribution looks like this. Okay, where in the shaded portion here you will have your particles with enough energy to react in a graph of number of molecules versus the molecular energy. Now, if you change the temperature, and temperature is a very important factor, so if there's any question that is asking you about temperature, you need to take the time to understand, are you dealing with gases? Okay, so if you're dealing with gases, then your Boltzmann distribution will change, because if there is low temperature, you have much less particles with enough energy to react. But if there is a higher temperatures, even if they did not have enough energy initially, the temperature gives them some energy, and then there will now be more reacting particles that are ready to react. Okay, but if you don't have gaseous reactants, the temperature again is still a very critical factor, because it will still act in increasing the rate of the reaction and how fast your reactants will collide with each other. The next part of this broad topic is now your dynamic equilibrium. And in dynamic equilibrium, the two opposing processes, that is the forward and the reverse reaction, will take place at equal rates. There are specific factors that can affect your equilibrium position. These will be concentration, temperature, and pressure in gas reactants. Okay, you can represent chemical equilibrium if you are representing, say, the concentration against time. Then you will have the the concentration of your products, of your reactants, starting at the very top, at the highest, and then coming down and then flattening and kind of becoming constant at equilibrium. And then the concentration of your products starting at the very smallest value, so the lowest value, and then climbing all the way up onto equilibrium where it becomes constant. So you have to remember this graph, and this was in your notes. Okay, so please make sure that you, especially now when I was marking your preliminaries, no one got this right. Okay, but it is there. You have to remember what has been given to you. Now, the rate, if you are given, or if you are asked to draw a rate of reaction against time, then you have the same situation initially. Again, your reactants will start at the high point, okay, and then your product at the lower point, and then as the reaction is going on, less and less reactants are available, and then more and more products are formed, and at equilibrium these two merge together and become constant, making a straight line. Okay, now Le Chatelier's principle comes in to help us explain the changes that happens when one of the factors are changed. Okay, and basically says that your system will now counteract or readjust to counteract the whatever that has changed, that is causing a change in your chemical reaction. Now, you can calculate the equilibrium constant of a chemical reaction at equilibrium by using the K, by using this formula over here. So we have a hypothetical equation over here, and there can be any unknown, a number of unknowns that can be asked in the question. So you need to be able to rearrange this equation in a way that will help you get what you want. So if you are looking for the equilibrium constant, then you will have your concentration of your products divided by the concentration of your reactants. Okay, if you are looking for the concentration of your reactants, then you will have your concentration of your products divided by your equilibrium constant. So you work your way around to figure out what you might be looking for. Usually you will be asked for the equilibrium constant. Now remember that when you are looking for the equilibrium constant, if you have any reactants or products that are pure liquids or pure solids, those do not come into your equilibrium constant formula. You only deal with your gaseous reactants and gaseous products in your equilibrium constant. Now, when you are calculating for your equilibrium constant, you need to take into account the next few points, and these points you will put them in a table. An example is in your lesson notes, and we will have more examples in our as we continue with our revisions. You will have your molar ratio for each of your reactants and your products that are formed, and then the amount of substance that was at the start of the reaction for your reactants. Obviously your products at this stage will be 0, and then the amount of substance at equilibrium. So what is left on your reactant side, and what is left on your and what has been formed on your product side. Now that change in the amount of substance you will use to figure out the concentration of each of these substances at equilibrium, and then this concentration can be placed into your equilibrium constant formula. So the steps are here. You have to take the time. You can't skip all of this. Okay, so usually the marks are allocated for each of these steps. So you have to show your molar ratio, you have to show the amount of substance at the start at equilibrium and the concentration of each of your substances at this equilibrium before you can now state your equilibrium constant. Second to last is our acids and bases. Now, acids are substances that will ionize completely in water to produce hydrogen ions. They can also be defined as proton donors, while bases are substances that ionize in water to form hydroxide ions, and they can also be called proton acceptors. Your ampholytes are substances that can act as both an acid or a base. A very simple example of an ampholyte is water. Okay, many of you could not state this. You have to remember at least one, and the simplest one is water. In a chemical reaction where you are dealing with acids and bases, you will usually have conjugate pairs in your reaction, where you have an acid and its conjugate base pair, and a base and its conjugate acid. You need to remember that whichever one has lost a hydrogen will be your acid. So if you pay attention to the hydrogen here, there is a loss of hydrogen from here to here, right? So that will be your acid and its base conjugate pair. And then the one that has gained a hydrogen will be your base and its conjugate acid pair. So you follow your hydrogen. Now, you also need to be able to describe how a neutral, an alkaline, and an acidic solution can be formed, and now relate this to the possible appropriate indicator that will be used for that specific reaction. So if you have a strong acid reacting with a strong base, you will form a neutral solution with a salt and water, right? And then the best indicator, you will want to pick the one that is the closest or within the range around 7, right? Because that is your neutral range. Now, if you have a strong base reacting with a weak acid, you are most likely going to produce a solution that is a little bit more on the alkaline side. So the best indicator, just by looking at this table here, will probably be phenolphthalein. Okay, and then if you have a strong acid reacting with a weak base, so you are most likely going to produce a solution that is more on the acidic side. So you will want to use an indicator that has a pH that is more on the acidic side. Okay, and probably your methyl red or bromo phenol blue over here, or even methyl orange. Now, how do you calculate for the pH of a solution? You can either use the negative log of your positive hydrogen ions or your positive hydronium ions. Another thing that I picked up on that you tend to get confused with is the different reactions that you can have with your acids and bases. Okay, so if you have an acid reacting with a metal hydroxide or a metal oxide, then you will be forming a salt and water. So generally, if you have an acid reacting with a base, you will always have salt and water. Okay, now the acid, if you have an acid reacting with a base that is a carbonate, that has a carbonate, either metal carbonate or metal hydrogen carbonate, you will have salt water and carbon dioxide. That's the only thing that changes between your normal acid base reaction and your carbonate ones. Now, if you have an acid reacting with ammonia, you will form a salt, and an acid reacting with just a metal, you will form a salt and hydrogen gas. Okay, you have to remember these. The last topic that was discussed and that we are going to mention very briefly here was the chloralkali industry. This is the overall reaction that is taking place in your chloralkali industry or equation. You will have the electrolysis of sodium chloride, and this will form sodium hydroxide, chlorine, and hydrogen. Each of these products have specific uses and very, very common uses. So you need to be able to state at least each. So for sodium hydroxide, this is usually used in soaps, dyes, petroleum products. Chlorine is used in disinfections and antiseptics. And your hydrogen is used in like your Haber process for nitrogen fixation, to produce methanol and to produce hydrochloric acid. That is also very useful in the chemical industry. Okay,